where I was having trouble with 113 hertz, my mixes might be overcompensating to make up for the frequencies that I'm not hearing in that dead zone. So my mixes would turn out to be bass heavy. And we're going to learn how to fix some of these issues, where the best to set up our list, where the potential of our room. Stay with it and we'll see you in part 2. In this video, we'll be learning all about the room. You're also going to need a few simple tools, such as a calculator and a tape measure. So the main goals for this video are going to be to discuss some of the challenges that we face in the home environment. We'll discuss the importance of room dimensions, and then apply some of this knowledge to find the best placement of the listening position within our room. In the field of acoustics, the room has one of the most profound impacts on the sound that we're hearing, or the sound that we think we're hearing. In fact, the room has such a huge impact on the sound that we're hearing that we could easily dedicate an entire video series just to explaining some of those concepts. And just to show you how much of an impact the room makes on your sound, here's an easy exercise you can try at home to increase your awareness of your surroundings. Just download some kind of on your smartphone. Then place the smartphone up to your ear with the talk piece facing outward. That way, it essentially records the same audio that your ear would be hearing. Next, walk around from room to room recording your voice with your voice depending on which room you're in. Here, take a listen to my recording. Take especially of the difference in the spaciousness of the frequency response. This is the sound of the listening position. This is the sound in the bathroom. This is the sound in the large bed. The sound in the empty guest bedroom. The sound in the hallway. This is the sound large, tall, living echo. And this is you can hear the long, high-frequency decay. Is of the sound of each room. It's not only of the direct sound that we're hearing, indirect sound, which is just as important. Oftentimes, our brain just blocks out these indirect sounds in order to focus on the direct sound. So again, this exercise is great for you to increase your awareness of your environment. So the first limitation for a lot of home studio owners is going to be space. When it comes to the ideal listening environment, room dimensions play one of the biggest factors. Some basic rules of thumb in acoustics is that larger rooms are better than small rooms, and rectangular rooms are better than square rooms. There are several reasons for this, but the main reasons have to do with the power of an audio wave, the shape of the room, and also the wavelength, or the distance it takes for a wave of a particular frequency to complete a full cycle. And one of the main deciding factors on room dimensions is going to be how reflections work. Sound reflections can cause all sorts of different problems, including an issue that we saw in the last video, which was the Haas effect. But reflections can also, in just a little bit, high wavelength is important as it comes to room dimensions. So you'll recall that our wavelength equation. You'll also recall from a previous video how if two audio waves that have the same wavelength line up with each other, their power all of this information relating to room dimensions. So at this point, everything should start making sense. Every room has 3 measurable dimensions. We have length, width, and height. And within these measurements, we can fit a full single period wavelength, which means for each one of these measurements, there's a single frequency that's going to react within the confines of that measurement. So let's break it down. In the home studio, we're often faced with having to deal with parallel walls. And in most cases, we're all dealing with some type of 4-sided room, which leaves us with either square rooms or rectangular rooms. Square rooms, where we have at least 4 sides that are the same length, will share common measurements and therefore share a wavelength that can fit between at least 2 of those dimensions. When these wavelengths resonate between 2 sets of parallel walls, since the wavelengths are the same, they can collide and have an additive effect. Since rectangular rooms don't share the same dimensions, we don't have dimensions resonating at the same frequency, creating that additive effect. So first, let's take at the standing wave, direct result of reflection. You should recall from a previous video that when a wave reflects off from a surface, it does so in an equal and opposite angle. And this is the main reason why rooms with parallel walls tend to have some of the worst issues with standing waves. These waves just ping-pong back and forth. And a standing wave is kind of unique in the fact that it doesn't really move. It's back onto itself and kind of just gets stuck in midair in synchronicity. These waves cause resonance, and the frequency based on the room dimensions, and these are our room modes. So the modes are just a fancy term for the frequency you're having problems with if you have parallel walls. So by using our wavelength calculation, we can measure the distance between the two walls and then figure out which wavelength would exactly fit within that distance. So measurement here. The thing we have to figure out is our conversion, because we're using feet per second to measure the speed of sound. So we take 1,126 feet per second and multiply, since there's 12 inches in a foot. That gives us 13,512, 119. And we get roughly 113.5 hertz. So that's really just one of the frequencies that a room is going to react very heavily. For instance, when I play this particular frequency in my room, but if I raise the frequency so the whole point of this isn't just to show you the shoddy construction of my door, that sound does create a physical manifestation in your listening environment. And it happens regardless. I hear a couple of places where the sound goes almost completely dead. These dead zones are what we call, when we look at a graph of our waveform, a node is the spot where the amplitude of the least. That just happens to be at our zero crossing. These nodes occur at half wavelengths. So if I was to divide my room in half, we could expect there to be a dead spot between